Okay, welcome again. Again, what I'm doing is I'm going over answers. This is going to be the 2017 number 4 FRQ. This is a no calculator question. So let's go ahead and get right into it. Taking a look at the problem, we see the ever important table of values here. And so in the table of values, what I instantaneously think of what I'm going to be doing in this problem is I'm going to be probably taking some Riemann sums. I'm going to be probably taking like an average rate of change between two of these values, and I'll also probably have to understand what the heck these values mean. On the bottom, it's all going to be fair game. Alright, so in this one, I'm just going to kind of read the basics and then get right down to it. Okay, so the first one says the function f, okay, we're talking about f, satisfies that f of 0 is equal to 20. Okay, so this is an initial value. They gave me a concrete point somewhere on this picture. The first derivative of f satisfies that the inequality is 0 to 7 of f prime. So that means this is always going to be positive. It's going to be less than 7, so it's always going to be going uphill. This f is always going to be uphill from 0 to 7. We'll get into that a little bit later. Okay, for all values of x enclosed on 0 to 6. Okay, so 0 to 7 from 0 to 6. Okay, selected values of f prime. So this is the derivative, not the f itself. The derivative is shown. So these are slopes all along the way. The function f has a continuous second derivative of for all real numbers. That just means that's kind of indicating that this isn't a weird graph that jumps around. There is no discontinuities anywhere along the way. It's all just a smooth picture, and it's all good from 0 to 6. It's all good. Okay, so there's nothing super fancy or weird that you have to kind of think about. Okay, question A. Use the midpoint Riemann sum. Okay, that's one that we don't usually use, but okay, whatever. Midpoint Riemann sum with 3 subintervals of equal length indicated by the data of the table to approximate f of 6. Alright, so here's the idea of this midpoint Riemann sum, okay, because usually midpoint isn't usually what we talk about. And also, if we do this, usually we're talking about something that probably has like 6 subintervals, but this only has 3 subintervals, okay, but for good reason. So if I'm going from 0 to 6, and I need 3 subintervals, I'm breaking this 6 up into 3 equal-sized spaces, that would indicate that this first rectangle is 0 to 2. The middle rectangle would be 2 to 4, and the third rectangle would be 4 to 6. Those are the 3 indicated values. So the midpoint, for instance, would be at 1, which has a height of 3, 5. Midpoint is at 3, which is 0, 8, and midpoint is at 5, which is 5, 8. So the midpoint is indicating the height of that indicated rectangle to satisfy a Riemann sum. Now, why the heck are they having me take a Riemann sum in the first place? Well, notice that this is the derivative. So here's kind of explaining what I mean to kind of get this ball rolling. Okay, so to kind of get this ball rolling, what we know is if I take the integral, okay, the integral from, let's say, 0 to 6 of a derivative, what the heck is that? Why do I take an integral of this? Is the net change. Okay, this is the change from 0 to 6. It will tell me how much that thing changes. It's the net change. Alright? So the net change. And this is going to be very important. Okay? So the net change. Well, how do they want me to take this integral? Well, this is just an approximation using my midpoint Riemann. So again, rectangles, three spots. So the first rectangle goes from 0 to 2, so it has a base of 2. 0 to 2. And a height of the midpoint, which would be at 3, 5. So that's subinterval 1 plus subinterval 2 is this 2 to 4. So 2 to 4 has a base of 2, a height of 0, 8. All right, last but not least is this 4 to 6. The midpoint 5 has a height of 5, 8. So base times height, base times height, base times height. All right, putting this all together, this is 7, this is 1.6, this is 11.6, 11.6, 1.6, 7 is going to be 20.2. Okay, now, net change. That means if I start at 0 and I go to 6, it's going to change a positive 20.2. So, if I start at 0, I'm going to change, and I'm going to end up at f of 6. Taking this initial condition into apply, we know that f of 0 is indeed 20. So I see that it is indeed 20. I just showed that my net change is 20.2. And so f of 6 is approximated, because this is a Riemann sum, it's an approximation of 40.2. Okay, that's my approximation of f of 6. Next, determine whether the actual value of f of 6 could be, potentially, 70. Explain your reasoning. Woo, how do you even get started here? Well, this is simpler than what it looks, all right? And it's simpler than what it looks. And the key to success in this problem is to see that my derivative is limited to 7. Okay, so the biggest it could possibly be is 7. So what does that mean? Well, think of how I set up this integral right here, the net change. So in B, this is A, B. So I know that the net change in f of x, how does f actually change? From 0 to 6 is f prime. Okay, well, what is this if, I'll just give it its biggest possible value. Okay, due to f prime is less than or equal to 7, I'm just going to assume that it's going to be the biggest. Let's just assume. So that would be saying, if this is f prime, that this is consistently 7. I'm just going to assume that it's always 7. So what is the integral from 0 to 6? Well, that would just be base times height. Now, is it 7? No, it's not always 7, but it could be less than that. So the biggest, absolutely biggest area that this could possibly be is 42. So what does that mean? Well, again, we're going to break this down. Oh, snap. I guess I was off the camera. My bad, I'm sorry. So the net change, this area is the biggest it could possibly be is 42. Okay, the integral, base times height, area under the curve, has to be, the biggest it can be 42. So breaking it down into a similar fashion as I did right here, so if I know that f of 0, and I'm going to change, my net change, is going to be f of 6, okay, I know that this is 20, and the biggest this can absolutely be is 42. So is it 42? No, it's probably something smaller than that. All right? But let's just see what this could, biggest it can potentially be. The biggest this could potentially be is 62. So f of 6 is absolutely less than 70. All right, so determine whether the actual value of f of 6 could be 70. No, my friend. Okay, why? How do I know that? Well, I know that because f prime of 7 is that means this has to be less than or equal to. Okay, because this is less than or equal to. Okay, that's why. And so this it just absolutely cannot be equal to. Okay. All right. Moving forward. Question C. Okay. On the open intervals, if any, is the graph of G oh, that's number 3. Like, what the hell? I already did that problem. Let's get to a new problem. Sorry. Evaluate 2 to 4 of f double prime of x. 2 to 4 of f double prime of x. Yeah, f double prime of x. Okay. So, C, integral 2 to 4 of f double prime of x dx is just going to be, oh, okay, so, like I forgot how to do this for just for a second. No worries. Here we go. So what's the integral of a derivative? Well, it just goes back one derivative. So the integral of a double prime is just a single prime. So the integral is this. But because it's a definite, I have to evaluate it from 2 to 4. So that means this is going to be f prime of 4 minus f prime of 2. To the table. F prime of 4 is 1.7. F prime of 2 is 2. Negative 0.3. Alright, 0.3. That is what the second derivative, integral 2 to 4, second derivative, etc., etc. And the last but not least, D. Okay, we have the limit as x goes to 0 of this function right here. Oh, right, I kind of smell where this is going. And it's L'Hopital. So let's just see here, though. Limit x goes to 0, f of x minus 20e to the x, 0.5, a half of f of x, minus 10. All right, let's just plug in 0 here. Okay, so let's just plug. So that would be this numerator. Okay, the numerator is equal to, this is when x is equal to 0, will be f of 0 minus 20 e to the 0. All right, that initial condition is going to be 20. E to the 0 is 1, so this is 20 times 1. 0. Okay. The denominator would be 0.5 f of 0 minus 10. Okay, so if this, again, the initial condition is 20, f of 0 is equal to 20. 1/2 of 20 is 10, so this is 10 minus 10, which is 0. Okay, so we have a limit of 0 over 0. Okay, so when you have a limit as when the numerator goes to 0 and the denominator goes to 0, you can use L'Hopital's. Okay, again, I don't know if you really recall what L'Hopital's is. That is that this limit is going to be equal to the limit as x goes to 0 of this derivative, of the numerator's derivative and the denominator's derivative. Don't think of it as being conjoined, but derivative of top and the derivative of the bottom. So like n prime and d prime. All right, so this is 0, 0. This also works if it's infinity over infinity or negative infinity over negative infinity. These have to be the same, and they have to be infinities or zeros. Okay, so L'Hopital. I'm probably sure I misspelt that. L'Hopital. It says that this because of that, numerator 0, denominator 0, is equal to derivative of the top, so that would be f prime minus e to the x is e to the x, so nothing changes. Derivative of the bottom, so this is 0.5 f prime. 10 goes away, because the derivative of 10 is 0. So now let's investigate what this is. And again, this can go all day. We can take the derivative of this if we get a similar situation as we did up here. So let's take a look at like n prime at x is equal to 0. And so that would be f prime of 0. So f prime, let's dig this back out. F prime of 0 is 4. Kind of jumping a little ahead of myself here. E to the 0 is 1, so this is going to be minus 20. Okay, so stuff's happening. F prime of 0, again, that's 4, so 1/2 of 4 is 2. So this is going to be negative 16 over 2, negative 8. So this limit is now equal to negative 8 because the original limit didn't really go anywhere. It got a 0 over 0. L'Hopital says we can take the derivative of it and do it again. So this should be d prime x is equal to 0. Goes right there. Okay. So that is L'Hopital's. I don't think this is going to be on this year's AP exam, but it's always good to know. All right. So that is that. Again, if you have any questions, ask me on my WebEx meeting, or you can just leave it in the questions box of the attendance check-in tab.